Hey everyone, welcome to another Sage tutorial video. Today we're going to be talking about artificial intelligence, what it is, its various uses, pros and cons. So let's jump right in there. This tutorial is really meant for beginners, people that know a little bit about artificial intelligence, have heard about it. We're going to touch on a lot of keywords, and let's get right in there. There's a lot of terminology that goes around with artificial intelligence. We're going to try and touch on those words. Different people refer to different things using the same terminology, algorithms, autonomous neural networks. We're going to try and delve into as many of those as possible. So the first we want to talk about is machine learning and artificial intelligence are not new. They've actually been around a very long time, probably considered the father of machine learning. Someone by the name of Alan Turing had a famous quote, "What we want is machines that could learn from experience." And this was back in the 1940s. So a lot of machine learning is math-based. That math has been around a long time. I think the applications now are just coming to light. So let's see. We're going to go through 8 different topics of machine learning. Okay? First thing we're going to talk about is big data. Okay? Machine learning only came about, or the need came about, after humans started gathering large data sets. They could be things like DNA sequencing or medical records being digitized. So now we have millions of people's medical records. Stock market data, what every stock did every second of every day for the last 10 years. That's a tremendous amount of data. The Library of Congress has not so recently scanned every single book. So now we have tons of digital literature, speech, weather data. So let's see how machine learning interplays with big data. So I'm gonna give an example. In my family, we have high cholesterol, so we're always conscious of that. So it used to be in the olden days, we would go to the doctor and he would want to know, am I susceptible to having a heart attack? So he would look at your age, maybe your gender, adult male above the age of 65, more likely to have a heart attack. And that was pretty much, how it went. We started getting a little more knowledgeable in the medical field. We started taking into account cholesterol. Okay, if you have high cholesterol and you're a male above the age of 65, you're likely to have a heart attack. But we still didn't have really concrete yeses or nos, or at least better percentages, 60%, 70%, 80%, 90% chance. And as we started gathering more and more data, it became harder and harder for a doctor, in this example, to predict whether or not you're going to have a heart attack. We could take into account your DNA, your history, your race, your height, your weight. All these different factors do play into heart conditions. How is a doctor, or science in that matter, able to take all this vast amounts of information and use it to try and find out whether or not a person is likely to have a heart attack? So we use something called a neural network, and this is how machine learning works. We start with all of the criteria of our big data. In this case, just to keep it simple, we picked 4 in this example. We'll take your cholesterol, your gender, your height, and your age, and we're going to call those the inputs. And the goal of the neural network, or the machine learning, as we'll see is referred to, is to determine whether or not a person with these 4 inputs is or is not going to have a heart attack. And the first thing the neural network is going to do is it's going to develop weights. We want to see how important each one of these factors is. How important is cholesterol? How important is your gender? How important is your height? And how important is your age? Off the top of our heads, we know cholesterol is pretty important in terms of for determining heart disease. Gender does play a role. Height, not such a role. And age does play a role. As you get older, you're more susceptible to heart conditions. So these weights are going to vary depending on the input. So weight 1 is going to be higher because it's by cholesterol. So we're going to multiply the weights by the input. So we might multiply your cholesterol by a high number. So if you have high cholesterol, it will become much higher. We might multiply your height by a little number to show that we don't really care so much about your height. We might even multiply it by a negative number to say it's actually irrelevant and we don't want to take it into account. But then we add up all of those multiplications together and we get a number. We could add a bias to it. We might talk about that a little later to increase the number, kind of like curving on a test. And then we have an activation. Either you're above a certain number or you're below a certain number, and that will determine whether or not you do or do not have a heart attack. So this is a very general, as we started with, we're using math, multiplication, a neural network is the simplest type of machine learning, to take large data sets, in this case medical records, to determine whether or not you're going to have a heart attack. And even just these four inputs we're using, cholesterol, gender, height, and age, would be almost impossible for a doctor to come up with a percentage chance of you having a heart attack. And imagine taking 15, 20 different medical data points into play. A neural network now has the capability to say, within a percent degree, how likely you are to have a specific disease or an illness. So remember now, big data is what leads to machine learning. And we're going to come back to that a lot, as we're going to see that data is really the crucial part of machine learning. All right, let's move on to topic number 2. We're going to talk about the types of machine learning. All right, and don't worry, we're going to come back to what we just spoke about. So don't worry if you're a little confused. We're just jumping right in there. So there's two main types of machine learning. The first one is called supervised learning. Supervised learning is what we just spoke about in our heart disease example. We know the answers to the question. We have 1 million people that have had heart attacks, and we have all of their medical data. So we know which characteristics lead to heart attacks. We have the answers. Okay, or for example, weather prediction. We know when the temperature, the humidity, the cloud cover, and 15 other environmental factors equal this, it's going to rain. We have the answers already, and now we want to extrapolate that into future predictions. We call that supervised learning, and it's the most common. We're taking data that we already have and trying to decipher new data that we input into the machine. The second thing is called unsupervised learning. Unsupervised learning is where I don't have answers. This is very common in vaccine and medical research. I have 1 million proteins. Find me common characteristics and put the proteins in different categories. So I say, hey, these proteins all have this specific amino acid, and these all have this specific amino acid. It turns out all of these proteins are associated with these types of viruses. So we don't necessarily have the answers, but we're using machine learning to categorize our data. Again, it's always with big data. It's just what kind of data do we have and what are we trying to do with that data. The third type is called reinforced learning. I don't have answers. I actually have a goal. And this is very common in autonomous driving, as we'll see, in robot development, even in learning how to play games. We're just going to tell a robot the goal. Get from point A, B. So in this example of a walking robot, we might give it a hip, a knee, and an ankle. Then we'll say get from point A to point B. And it'll try and move its hip and then its ankle and put its hip down and realize it didn't go anywhere. It might bend its knee first and then fall over and realize, oh, I can't move my knee first. Eventually realize its hip, knee, ankle, and then back down at the hip, how to take a step. And it can go through this process millions and millions of times till it refines its most efficient method. But this is called reinforced learning. We're not telling it how to do it. We're not telling it a solution. We're telling it a goal. So example, let's say we're trying to teach a computer how to play chess. We might start with supervised learning. We'll input all of the grandmaster moves for the last 20 years. So whenever A, B, and C happen, the grandmaster always moves piece D. So the machine will now realize that whenever A, B, and C happens, I should move piece D. But we could also mix in with their reinforced learning. Why doesn't the computer now try every single possible move and see which one will lead to a better position? So we could start with supervised learning and then bring in reinforced learning to allow the machine to try multiple different possibilities to try the most efficient, or in this case, most winning move. So those are the three main ways that machine learns. It always involves big data, and it usually involves with the type of data we have determines the type of learning we're going to do. We'll give some more practical examples that always helps people understand a little bit better. First, let's talk about unsupervised learning. So where do we have that? In a Google search. Everyone knows when you start typing, Google will finish off what you're typing. So where do those suggestions come from? So that's called unsupervised learning. Google sees whenever anyone types A, B, and C, they also type D. Let's put that together in a group, A, B, C, and D. That's unsupervised learning. We didn't tell Google what we want to search for. It just sees patterns in what people type. Another one will be genome classification, or in this case, I'll give you a simple example of dogs. Here's a picture of 10 million dogs. Tell me what kind of dog categories are there? We know there's poodles and labradoodles. I don't even know, but perhaps the machine learning can find other categories that we didn't even realize. 10% of dogs have floppy ears, and 10% of dogs have little wet black noses. I don't know, but we're allowing the machine to categorize the data instead of us telling it the categories. The last thing is a lot of human demographics. We as people will see kind of have our own connotations in how we want to apply demographics. So we might do by gender, by income, by geographics, but the machine learning might see other efficiencies that we don't. For example, you might input all of the demographic data for the students in the school and see that GPA plays a big demographic. We have really low and really high. Or synagogue affiliation. We have big groups from very specific synagogues. So there's a lot of demographics or choreographing of data that we might not see as humans that the machine learning could pull out. Next, the most popular is supervised learning. Very popular now with speech to text. It's on just about every device. So we gave the computer millions and millions of hours and hours of speech and text, and now it could then take that data and now extrapolate when I give it new speech, what text am I trying to say? The stock market is very popular. There's a lot of companies now that really just use machine learning for investments. They come into the office in the morning, turn on the computer, and it just starts trading stocks. It takes into account all the previous stock data. When A, B, and C happen, the stock went up. So if A, B, and C happens again, let the stock go up. And it's more complicated. It's not just A, B, and C. It could be 100 different inputs that determine whether or not a stock will go up and down. Also trying to mimic motion. The Wii remote was one of the first devices that came out that did that. But let's say you're playing sports and you have an Apple Watch. How does the Apple Watch know when you're swinging a tennis racket or when you're jogging? So it was fed thousands of hours of people jogging and thousands of hours of people playing tennis. And now it knows whenever anyone goes like this, it's associated with the tennis person. So that's supervised learning. We fed the machine learning the data that we already knew what it was doing, and now when it sees that data again, it could figure out what's going on. And reinforced learning, we're going to delve into this a little more later, but self-driving cars. We spoke about learning chess and learning and for robots how to walk. So these are the main types. The most common one that we as users come into play with, especially our children, the students, is supervised learning. We gather data, we input it into the computer, and then we ask the computer to find similar patterns in our new data. Let's go through some quick examples. The Nest learning thermostat. So you program the temperature that you like, and over time the thermostat figures out whether or not, at 5 o'clock you like it this temperature, at 8 a.m. you like it this temperature. So that's supervised learning. It spends a few days and a few weeks gathering your data, and then it tries to mimic that over time. Another example we all come into contact with every day without even realizing is retail shopping suggestions. So in this case, customer 1 bought bread, looks like some water, an apple, and a head of lettuce. Customer 2 bought another bottle of some sort of juice, apple, and bread. Customer 3 comes onto Amazon and puts a loaf of bread in their cart. What should Amazon suggest? So this is unsupervised learning. It's trying to group other previous customers' shopping carts together and try and say, whenever anyone bought bread, they also bought a bottle of water or something like that. Another very, very common is ChatGPT. If you haven't used it yet, you should be. It's fabulous. Students are all using it. Most offices are using it at this point. ChatGPT is supervised learning. We gave it all the information. We gave it millions and millions and millions of lines of text. And now when we type text, it could associate that text, what it's trying to interpret based on other texts that it's seen. There is a little more to it. These are called large language modules, LLMs. They kind of have multiple machine learning algorithms going at the same time, because it's really fabulous what they're discovering with the English language, or what they're documenting, how different words mean different things when they're near different words, and sarcasm. Really great stuff. So that's large learning modules, we call that, but it is in the branch of supervised learning. Very popular now is art. So we have on the left was you fed your model a bunch of Picassos, and then it spit out similar Picassos. So that would be supervised learning. On the right, this is by Refik. It's actually in the MoMA. These are giant displays. They're like the size of the whole wall. It's unsupervised. He fed it. This is how you make color. These are lines and circles. You just spread the color out, and the machine learning looked at different patterns um, throughout the art that was fed to it, and said, "Oh, I could just categorize whenever there's blue. It's usually next to red and things like that." So it's not necessarily. It has some context of supervised because you did feed it data, but you didn't feed it what the right and wrong answer is, and that's the difference. Um, and here's through the senior. This one's a pretty popular picture going around right now by Runflow. I'm sorry. He does AI art, really popular. So here he has a rabbi and a soldier hugging. This is not a real picture. I don't know the exact terminology that they use to make this art. Probably rabbi, soldier hugging, something like that. Some keen eyes. How do you know that this is an artificial intelligence generated graphic? You might use logic and say this an odd thing to happen in front of a cement wall. You could also see there's some nuances when the computer doesn't always know all the details to life that we as human beings know. For example, the soldier has two guns. I don't think soldiers carry two guns. This I didn't know. The gun in the back is pointed up. Soldiers have told me that the gun in the back is supposed to be pointed down. Someone mentioned the ski goggles are not real soldier goggles. They're just goggles. The computer was trying to figure out that all rabbis wear black hats, but it wasn't really sure what a black hat was. The brim is actually like a 1 inch thick hard disk. And that's actually not how black hats are. But you could see that taking from pictures that it was fed, it was able to determine what a rabbi was. They usually have beards. They usually wear black and white. Soldiers are in green. They have guns. Hugging is when two people have arms wrapped around each other. So that was all data that it was able to glean from pictures that it was fed. But just to see what's out there, really, really great stuff happening. All right, so now let's talk about gathering data. Um, Probably one of the most crucial parts of a successful machine learning project is getting the data. Um, a lot of lower and middle schools do this kind of machine learning aspect. It's kind of before the heavy coding. It's let's get some good data. A long time ago, at this point, 7 years in machine learning, well, 8 years now in machine learning is like forever ago. Google came out with something called Quick Draw. It was a little bit of a game, and I'll show you a demo here now, where people had to draw doodles. And what they needed was data. They wanted to teach the computer how to draw, how to identify all these doodles. And the only way to do it was to have people draw doodles. And they made a little bit of a game. And so I'll show you, they have hundreds of thousands of pictures. So this is the bulldozer example. So they had hundreds of thousands of people drawing bulldozers. They made it into a little game. They gamified it. The computer would try and guess. You could play it now. The computer will try and guess while you are playing what you were drawing. And while you think you were playing a game, you were actually providing Google with their data. And we're going to see later on, a lot of what we do is actually companies that just gathering data from us. So now Google has a new program, not their most biggest piece of software, not like Gmail or Google Search, but a thing called Auto Draw, where you draw and it will tell you what you're trying to draw. In this case, first guess was a bicycle. Second guess is a pair of glasses. Seems like a pair of glasses. That's a good guess. Third guess we have here was some drums, and then a key, maybe an apple, a cake. But it was pretty accurate in guessing a bicycle and then glasses. And that was from hundreds of thousands of people drawing glasses and bicycles. And then the machine learning algorithm is able to say, oh, this is similar. When someone drew two circles with a line in the middle and a line on top, they usually meant a bicycle. And that's how gathering data plays a crucial part in machine learning. And you're welcome to try this. Both of these programs are still available for public consumption by Google. The next thing I want to talk about is the value is in the data. This is really something that we as consumers are becoming more aware of. What's happening to our data, what companies are doing with our data. Really fascinating stuff. So data is a business. If you don't pay for it, you're the product. So think about how much technology we use for free. Gmail, Google, Waze, Amazon, just the search part. I know we pay for the products. But think about how much technology we use every day for free. How many websites do we go to? CNN.com for free. Anytime you're going to something for free, the company is benefiting from you, and usually that's in the form of gathering your data. Waze was one of the first companies to really spearhead this or discover this. I remember about 13 years ago buying my brother-in-law a Garmin GPS for like $150. I owed him a big present. So I bought him that, and a few weeks later, Waze came out, and all of a sudden, everyone had free GPS, which was weird because you used to have to pay a lot of money for GPS, over $100 for GPS, and Waze was just giving it out for free. And everyone's like, "Well, how does that work? It costs them money to develop this app, to make this app." And what people didn't realize at the time, what industry didn't realize, and what Waze realized was, we're actually going to know all the traffic data for every street in America, now in the world, at every second. That data is invaluable to know the speed of traffic on every block at every second. That data is worth much more than the $150 I paid for the Garmin. Think about who they could sell that data to, what municipalities they could sell that data to, what businesses could value from that data. And to this day, Waze hasn't fully figured it out. Neither has Google, who bought Waze for billions of dollars. But they're still trying to figure it out, but they see the value in data. We have a tremendous amount of information, and we'll see some more examples where that's actually more valuable than the company itself. Another lesser known example is Tesla. People think, what's Tesla do? They make electric cars. The car business in America is not very successful, even for Tesla. Every quarter is, I don't know if you own Tesla stock, every quarter is kind of win or loss. Will they make money this quarter? They not. They've had a few winning quarters in a row. It's not this mega company where they're just printing money. It's hard. They work really hard to cut down on to make the company more efficient, to produce cars, but it's hard to make cars in America for profit. It's not a great business as we've seen. So what's Tesla doing? Well, what's their real value? If Tesla stopped making cars today, they would still be a really valuable company. And that's because their data. Tesla knows exactly how everyone drives, when people need to maintain their cars, how driver technique, speed, and aggressiveness affects car maintenance. They have all of that data. Another thing they do, which is, I guess in the news more, is autonomous driving. So this is how autonomous driving works. A car, different companies use different sensors, but essentially the car is trying to get a picture of the world. It might use LiDAR or radar or sonar or cameras, all different types of sensors, but they're trying to get a picture of the world. So in this case, we have an intersection. We have two cars stopped in front of us. We have a red light. We have in the background a green person, computer identified a person. We have a yellow car going across the screen. So what do you do in this case? So as a person driving the car, you see the person's far away. It's not an emergency. It's a red light. I slow down. I don't have to slam on the brakes. I would slowly come to a stop. So this is something that happens all the time when we're driving. We come up with thousands of scenarios very similar to this, and as humans, we figure out what to do in each scenario. And that's what autonomous driving is trying to do, to figure out every single possible scenario. And then we know to tell the car when scenario 7,403 happens, slow down, make a right turn, make a left turn. There's a lot of scenarios. And whoever has the most data or has undergone the most scenarios has the most capable self-driving cars. In this case, I don't want to say it is Tesla. Tesla definitely has the most advanced autonomous vehicles. But it's not the vehicle itself that's so advanced. Yes, this is an electric car, but it's that they have the most data on how to drive. And that's really a bigger business than making their cars. Another business that just recently happened a few weeks ago was the New York Times sued ChatGPT. It turns out that ChatGPT was using New York Times articles, just English. ChatGPT needed English in order to determine what we type, what we need. It needed already written English to put sentences together, and it fed in all the New York Times archives. And the New York Times now saying, well, you used our information, our data, to build your ChatGPT, your machine learning system, and you should pay us billions of dollars for that. And it's likely going to take months and years, and this is probably going to go to the Supreme Court. But what's fascinating is that it could be that the raw text of the New York Times, just the data itself, could actually be worth more than the news. I think the news is like $1 a week or something. The just well written English, millions and millions of lines of well written English could actually be worth more to the New York Times than the news that they're printing. So we're really seeing companies. It's not so well known, but appreciating the value of the data they have, sometimes more so than the product they're selling or even giving away for free. So be aware. Everyone's like, "Oh, secure my data. Don't let anyone have my data." I'm not saying good or bad, but the companies are trying to get our data. That is of value to them. Our shopping habits, our driving habits, these are all value. Is it wrong of them to take it? Well, that's up to you to decide. So now let's talk about bias. You can't talk about machine learning without talking about bias in machine learning. And we'll see why maybe bias isn't the best word. So we had our heart attack scenario. We had all our different parameters. So let's say I put in all the information from everyone in America. Would it be 100% perfect at telling me that I'm going to have a heart attack? What if I use 5,000 people? Then I did the same exact model, but I used a different 5,000 people. So would my model then predict my heart attack the same way? Would it be just as accurate? What if I gave it every single person in the world's data? Would it then be good at then determining every single person that ever had a heart attack? I knew all of their medical information. Would my computer then be good at predicting a heart attack? Maybe yes, maybe no. It could be that not everyone's the same as me. Americans might have a different eating habit than Asians. So inputting American medical data might not be good at predicting an Asian person's heart condition. And that's called a bias. There's no such thing as machine learning without bias. If a human made it, it's biased to that person. Now, I don't say the reason I don't like dealing with bias kind of has this negative connotation to it. It can be negative. It's also just we're people with experiences. And so when we make something, those experiences come to play. There's training data bias. So let's say I only had medical data for old people, or I only had medical data for a certain for wealthy people, or I only had data for city people. We see this a lot with polling for elections. They'll poll a certain area, or they'll poll a certain demographic, the people that answer the phone at 5 o'clock and are willing to talk to you, a certain age bracket. So it is biased because they're only gathering a certain type of data. And that's not necessarily that they're trying to be biased. It's just if you're trying to find out who people want to vote for at 5 o'clock in the afternoon, there's only a few types of people that might answer the phone and tell you that data. So there's always training data bias. And sometimes we're not aware of it. And that's the tricky part. Algorithmic bias. So that is when the scientist or the engineer actually unknowingly tweaks the model to try and get it more accurate, but is actually instilling bias. So in our heart disease example, we might say, like, for sure, put emphasis on cholesterol. That's definitely a big factor in heart disease. For sure, put an emphasis on blood pressure. We might say for sure put an emphasis on age, and perhaps age isn't a factor. Perhaps we'd be able to find heart disease much younger if we wouldn't bias it by assuming that old people are more likely to have heart attacks. So these are things that the engineers or the computer scientists might unknowingly instill in their algorithms. The last most common one is cognitive bias. This is more based on just our human experiences. So with a heart disease, people, I think, assume, maybe they do, maybe they don't, that men are more likely to have heart attacks than women. I don't know if that's true. So that might be a cognitive bias that you might put into your machine algorithm by collecting more data from men, by questioning more men, by giving more weights to the male data without realizing that we're losing a whole group of female data that might actually help us predict medical issues by females. All right. So when talking about bias, we also compare it with variance. So let's say I was trying to train a machine learning model to predict whether or not I have a picture of a dog. All right. So I show it a picture of anything in the world, and I want it to know if it's a dog. So I have to show it. It's supervised learning. I show it a picture of a dog. So what happens is, because I have so little data, the machine is going to be super, super biased towards a dog, meaning anything that has two eyeballs and a nose, it's going to think it's a dog. It could be a person, it could be a monkey, it could be a cow. I've only shown it one picture. So it's going to assume that everything in the world is a dog. We call that bias, and there's very little variance. The flip side is supervariance. What if I'm looking for dogs and I give it a picture of every single animal in the world? So now it might think a dog is actually a coyote, maybe a Beethoven kind of dog might be like a little polar bear, like a little brown bear. So we're giving it too much variance in our supervised learning. So we call that overfitting, meaning it's trying to match our exact picture to something exactly that we've given it. And that's also a problem because we don't want it to think everything is a different animal. We do want it to kind of squeeze things into categories and say, oh, this looks like a dog, it is a dog. So when we have too much data, we call that overfitting. When we have not enough variance, we call that bias. All right, let's go through some examples here. This is Tesla. They're into machine learning. They got great examples out there. So this is someone's auto driving, and they have the screen in front of them, and there's a horse and buggy. Maybe they're in Amish country. I'm not sure where. And the first thing it does is it looks like the Tesla thinks that it's a semi truck about to crash into it. I guess the trunk of the wagon looks a little bit like the hood of a truck. Then it figures out it looks maybe like a car, and then it kind of looks like a sideways truck. So is this bias or variance? So it's not bias. It's not assuming that it's always the same thing. It's actually a lack of variance, and probably cognitive variance, where the engineers didn't think to train their autonomous vehicles to follow horse and buggies. Um, Sorry, I realize I am blocking the picture there. But okay, this is one of the first fatal car accidents Tesla had. There was also another one with a person crossing the street at night. But what happened was the car was driving autonomously and it literally plowed straight into a semi truck. Didn't even see it there. So there was a lot of studies. This again, autonomous vehicles are still up in the air. People are not 100% comfortable with it. So this is what the vehicle saw, and this is what it looked like in real life. So that big rectangle doesn't necessarily look like a truck. It looks a lot like the street. It looks a lot like the sky, and the algorithms in the Tesla autopilot did not assume that that was a truck. So this would also probably be a lack of variance. Um, a sky colored truck completely sideways just looks like a big chunk of the sky, and actually it's a truck. So that was again a lack of variance. Here's an example of bias. Indeed was trying to do machine algorithms to they're a job search site, so they were trying to find the best job candidates for their companies, the companies that are using them um, to find applicants. And it turns out that the most successful applicants were people with 4-year degrees and 5 years of experience. But in actuality, that's human bias because the best people for a job might not have those exact qualifications, but they might still be a great fit for your job. And it's tricky. So again, bias is not always a negative thing. Sometimes you're conscious of it and still don't know how to fix it, like in this Indeed example. But it's something that we need to be aware of as we use machine learning, as we develop machine learning. Everything has a bias because it was made by people. It was developed with a specific chunk of data. It's biased towards those people's feelings and towards that data. Um, Here's another example that came about kind of recent. I'm not sure. January 6th. I guess it's been like over a year. So if you had searched for Civil War, I don't know, maybe your child was doing a book report near the January 6th, January 8th riots at the Capitol. These are what Google was popping up. Not because Google is being biased, because this is what people are searching. So if someone else searched for Civil War, they would say, "Oh my gosh, the Civil War is coming! It's imminent! It's coming! It's right here!" They would think the country was being ripped apart. Maybe it was at the time, but this is a way that someone that wasn't aware of what was going on at the Capitol might be biased or might be influenced. I'm sorry, by what they're seeing at Google. Another example. I don't know the whole story behind this. There was a restaurant that had a rat, and a few people searched whether or not there was a rat issue. And now, whenever you type in that restaurant's name, Google automatically finishes with the word rats. I don't know if it was a one-time incident or this restaurant constantly has rats, but either way, it's definitely influenced people that search for the restaurant now automatically might assume that rats are there. It could be maybe only 100 people search for this website, for this restaurant. And 10 of those people, without even there being a rat incident, just want to know, are there rats there? And just by the fact that those 10% of people wanted to know if rats were there, Google now associates that restaurant with the word rats, forever blacklisting this restaurant when you search for it, for people now to assume that there's rats. There's always a lot of talk about election bias, election mingling. It is 100% a real thing. Who does it and when they're doing it and when they're doing it on purpose, that's up in the air, and there's always discussions and um, you know studies to try and figure out how we could stop it. But there is for sure influence on the internet. Um, Typing this restaurant and seeing the word rats, typing the word Joe Biden or Donald Trump, I guess Google's super aware of those. I think they'd be very careful of what they assume the next words will be. But for things that they're not so on top of, we're super influenced by what we see on the internet. We take that by fact. And Google's not even trying to influence us. They're just putting together groups of data that people have been using. And we are influenced by it. Bias is everywhere, and we have to be aware of it, and our children have to be aware of it. Okay, let's talk a little bit about the hierarchy, what artificial intelligence is. There's a lot of terminology out there. Let's just talk about it briefly. We've actually been mixing up these terms within this one presentation. We start with deep learning. So that was our heart attack example. We just take data. It's very similar to statistics. There are people that even call it statistics. It's actually more linear algebra, but we're taking data and we're just trying to find patterns in it. The next would be machine learning. This is more of we're taking that data and then based on our answers, we're actually refining our algorithms so that our results become better and better. That's probably the most common today. And then artificial intelligence is where we try and extrapolate and predict other things unrelated to our data. This is not a perfect example, but it's something to try and help relate to these. The original Google Translate, which was kind of funny, you could pay broken telephone, you could like translate English to Hebrew and then back to English, and you'd get like some jarbled, because it was just trying to figure out patterns in data. But we see now language is much more complicated than that. But that would be Google Translate. Machine learning would be an example of Google Search, where the more people used it, the more that people clicked on things, the algorithms got better and better at predicting what you wanted. There was a study that said no one ever checks the second page of their Google results. If it's not on the first page, they type in a new search. So as people clicked on links and typed in new words, Google got better and better at predicting what people wanted. And then Google Assistant, that's like Alexa or Siri, those types of technologies. They actually try and predict what we want, what kind of music we want to listen to, what kind of alarms we want, what we're shopping for, what we need to shop for. Those are already artificial intelligence. Again, these words are not set in stone, but in general, the industry uses these words to describe these technologies. The next thing I want to talk about, probably the hardest topic, is actually we're going to go a little bit into the math behind how machine learning classifies data and uses it to predict something. We're going to use a very simple example now. It might get a little. We'll see. See if we could understand what's going on. So we use a very simple, common example. I'm writing something, and I want the computer to tell me what number I'm writing. So I write the number, in this case, the number 9. And the first thing we need to do to our data is to break it down. So in this case, we're breaking down our data into a 28 by 28 grid into pixels. I think pixels are a well-known term. So I have 28 by 28. I have 784 inputs. So in a heart attack example, we had, I don't know, 10 or 15 different inputs. Just writing down the number 9 has 784 inputs. I mean, this is a pretty small screen. This is like a 1-inch by 1-inch screen, if that even. And then we need to give numerical values to our data. So in this case, each pixel is going to have a number from 0 to 1. 1 meaning the pixel is very white, and 0 meaning the pixel is very dark. So now we have 784 inputs, and we had to break down our data into numerical value. And that's important. I mean, any kind of data that you're feeding into a computer system, you have to break it down into numerical values, which is hard by language they're seeing, by the ChatGPT, by the large learning modules. It's not just numbers, word one comes after word two, it comes after word three. English language is pretty complex. The order of words affects the meaning of words. All right, but anyways, so we have 784 inputs and we have 10 outputs from 0 to 9. So I put in 784 pieces of data, and I want you to tell me, what number am I writing from 0 to 9? All right, so we're going to break this down even more with our number 3. Instead of discovering if I wrote the entire number 3, let's just look if I wrote the top of the number 3. And that's signified here by this orange box. So I just want to see whether or not I filled in the orange box. So I'm not looking at the whole number. The machine's just checking that one box. And now I'm going to put some pixel examples on the screen. So we have pixels 1, 2, 3, and 4. Those are inside the box. Pixels 5 and 6 are outside of the box. 7, 8, 9, and 10 are inside the box. And 11 and 12 are outside of the box. So just looking at the right side of the screen, pixels 1, 2, 3, and 4, 7, 8, 9, and 10 are really important in determining whether or not I wrote the top of a number 3, or I wrote in that area. Pixels 5 and 6, 11 and 12, those pixels are not important. Not only are they not important, they're actually negatively important. Because if I wrote there, it means I'm probably not writing the number 3. I might be writing the number 7, which has a much longer top. I might be making the letter T. So what I'm going to do now is I'm going to multiply each pixel by a number. We call those weights. So pixels 1, 2, 3, and 4, those are going to be multiplied by big numbers. Any whole number we consider big. In this case, number 2, 3, those are big numbers. Because if I wrote in those pixels, I'm going to multiply those pixels by big numbers, and I'm going to get even bigger numbers. Now, pixels 5 and 6, I'm multiplying by negative numbers. Because if I wrote in those pixels, I want it to be a low number. I want to lower my score because it means I'm not writing the number 3. So I actually want to give myself a lower score if I filled in pixels 5 and 6. Pixels 7, 8 are good for the number 3, so I'm going to multiply those by high numbers, and so on and so forth. All the pixels outside of this area, I'm also going to multiply by low numbers because I only want to know if I wrote the top of the number 3. So the pixels that coordinate with the top of the number 3, I'm going to multiply by high numbers. And if I filled in those pixels, I'm going to get a really high score. If I filled in other pixels, I'm going to lower my score, and I'll overall end up with a low score for the top of the number 3 test. Let's give one more example. I want to know if I wrote the number 8. Okay, so in this case, we're only going to look at the top half, the donut, the number 8. Why would I break it down like that? Perhaps what other numbers are associated with the top of a number 8? I might be making the number 9. There's also a circle at the top of a number 9. So we need to figure out how we want to even break down our areas. Am I only doing numbers? Am I also doing letters? The top of an 8 could also be the top of the letter P. So as we develop the algorithms, we also want to see that the part of developing machine learning is see how to break down the data. So here, all the pixels inside of this circle, if they're all filled in, there's a good chance I drew a circle. There's a bad chance I drew a diamond or a triangle. If I filled in all the pixels inside of this yellow circle, I'm probably not drawing a triangle. So what am I going to do? I'm going to take all of these pixels. Let's assume there's too many pixels in there to count, but 10, 11, 12, 13, 14, 15. Let's say that's the donut pixels. I'm going to multiply them by high numbers and add that into my circle area. And if those are filled in, and then I multiply them by high numbers, I'm going to get a really high circle score. And the computer's going to know Adam drew a circle there. I'm also going to multiply all those pixels by low numbers and put those in the triangle box. Because if I filled in all of those circles, in all the pixels in the circle, I do not have a triangle. So I want my triangle score to be low. So the blue lines represent positive numbers, and the red lines represent negative numbers. And the pixels 10, 11, 12, 13, 14, and 15 are the pixels within my circle. And if they're all filled out, it means I have a circle. And if they're all filled out, it means I do not have a triangle. And we can do this over and over in a lot of different areas of our drawing. And we start putting together different shapes. And now I could see if I have a circle and a line, I might have a 9. I might have that same line as the number 9, but if I put it with a number 9, another line, and another line, I might actually be drawing the number 4. So we call all of these neural networks in the middle, layers. And what our machine learning neural network looks like in real life is something like this. We have our 784 inputs, and on all the way on the right side, we have our 10 outputs. And what we're trying to do is take our 784 inputs, multiply them by thousands and thousands of weights. That's every single white haired line in the middle is a weight, and try and determine whether or not I drew the number 9. And so each step of the neural network or each layer is not determining what number I wrote or what letter, but it's determining perhaps one aspect of that number or letter. And then the next layer might be combining those different layers until finally I write the number 7 and I click on I click all the weights line up that at the end give the number 7 the highest numerical sum, right? After adding together all of those multiplications, and then we see that we wrote the number 7. We call this a neural network. I have to give credit to I forgot his name, Grant Sanderson. He has a fabulous YouTube channel called 3 Blue, 1 Brown. He makes high level math videos, probably college and graduate level math, calculus and above, let's say. And he has some fabulous videos on the math behind the determining the weights. We didn't discuss that here. We just discussed taking our data, multiplying by the weights will determine who wins in predicting what I wrote or the correct answer. But there's actually tremendous math that went to go backwards to determine what the weights are of each of those black lines on the screen. This math was done years and years ago. This was the early stages in the 40s and the 50s of machine learning, but it's linear algebra. I would recommend checking that out if you're more interested in learning about that. So now let's talk a little bit about our last topic we're going to discuss today. How do we access machine learning? Where do we use it? Could we use it? Who gets to use it? So it's not so simple. There's a lot of steps to machine learning. You need to train the module, so gather the data. You then need to convert that data into numerical values, like we saw with the number 9 over there. Design the network. So could I just go from my data to the number 7, or I'll actually be much more efficient and accurate if I break it down into circles and lines? So seeing similarities in numbers and letters, what lines and circles they have in common. The same thing with speech. What sounds the different words have in common that I could say, oh, you said ch. You might be saying Chicago. You might be saying chair. So we could break down words into different sounds, how many syllables are in a word. So that's all in designing your network. We then have to find the W's. We have to solve the network. We're going to talk about where that happens, but there's thousands of variables that need to be solved, all of those weights. And a good neural network will always be resolving those. We spoke about how Google's search algorithm is always making itself better and better. It's getting its results, seeing if it got it wrong or right, and then resolving for the W's inside the neural network so that the next time it gets the correct answer. The same thing we discussed when learning how to play chess. You then just need to code that for the specific platform that you're using it on. It might be on your phone, iOS or Android. A lot of servers might use Linux, a microcontroller, a smartwatch, things like that. And then you actually need to run your neural network. You need some sort of computer to run it. So there's a lot of steps to say like, oh, let's use machine learning. It's like, oh, a lot of like, I just saw a Shark Tank business. It's like, oh, we're going to use machine learning to predict what kind of dresses women want to try and buy. And the judges, the sharks were like, do you know there's like a lot that goes into that? You don't even have the data, let alone all of the middle steps to produce that. So there's a lot that goes into it. There are softwares that will do a lot of the steps for you. So perhaps you have data and you could dump it in there and it will figure out the rest of the steps. But the point being that it's not so easy to use necessarily. You also think you have to focus on is where the data is being processed. So when we train data, we usually do it on big servers. It's a lot of computing power. So what's that mean for, let's say, the original Google Translate? It would record your voice, make an audio file. Then it would have to send the audio file to Google servers. Then it would do the machine learning process, try and predict what you were trying to say, and then it would send it back to your phone and convert your spoken text message into text. It was slow, and we had to go. You needed to have good internet service first of all for that to happen. You had to send the data there and get the data back. So we try and do machine learning on the edge. We call that edge computing. The edge meaning the closer it is to the user, the better and more precise, more accurate, the quicker we can get it. So, for example, we have a smartwatch, an iWatch. It wants to determine your heart rate. So it's seeing the beats, the flow of blood, and based on the your flow of blood in the past, it can predict how much flow and what kind of flow will be considered a beat for you. So all that learning might happen on the Apple servers, but the multiplication, once we say, hey, we have a beat, multiply this by this weight, that could all happen on the edge, on the watch. So we just need to determine where we're training the model and where we're operating the model. And are we retraining the model? Does your watch then need to resend your data to the Apple server to retrain how you could find your specific heartbeat? So we do need to just be aware of where the data is happening, where it's being trained. A lot of chips now in iPhone and Android phones and smartwatches are the TensorFlow chips. I forgot the name of the Google chip that they're using. Their whole focus is designing a chip that will allow machine learning to happen locally. I don't know if anyone's aware, graphic cards are great at that. So there's a big run in the last few years on graphic cards, not because people are playing video games, but because they're great at processing all of these weights for machine learning. So we need to determine, can we process this on the edge, right on our phone, right on our smartwatch, or do we need some sort of server that we have to send our data to? And there is a lot of access to it now. So I hope this was insightful. At the very least, should brought some sort of awareness that we're using machine learning and AI everywhere in our lives nowadays. Spam detection, image recognition, shopping recognition. Every time we swipe our credit card is learning our habits to help predict fraud. Shopping suggestions, customer service now is trying to predict what we want before we even get to talk to someone. Health is monitoring us. Any website, any large corporate website they're using now, Twitter, YouTube, TikTok, Amazon, Google, ChatGPT, Instagram, the Weather Channel, are all using machine learning. More importantly than the fact that they're using machine learning is, if they're using machine learning, it means they're using our data and they're trying to gather our data. Perhaps it's good. Some people like when corporations gather their data. It makes the product better. But I hope this brought a little bit of enlightenment to you, to see what's out there, to see what's going on, a little bit of awareness. It's a fascinating field. It's really cutting edge. New tools are coming out every day to allow us, the users, the students in school, to use machine learning, for companies to get better at it, to get more efficient at it, to become more transparent at it. It's really a fabulous field. Thank you for your time. Have a great evening.